Hi everyone, I'm Charles, and I'm really excited today to present to you our work on the T-complexity costs of control flow and error-corrected quantum computation. Now I'm sure you agree that was a real doozy of a title, so let's break it down into its parts and see what I mean. First, what is a quantum computer and why do we want to build one? Well, in short, a quantum computer is a device that uses quantum information to solve problems faster than any classical computer can. What I mean by that is that we know of quantum algorithms that can deliver an asymptotic advantage in time complexity over classical algorithms for tasks ranging from factoring to linear algebra and physical simulation. And these quantum algorithms achieve this by exploiting quantum information. Whereas a classical bit can exist either as 0 or 1, a quantum bit or qubit exists as 0 and 1 at the same time. Now mathematically, a superposition is a linear combination of states 0 and 1. These coefficients are called amplitudes, and if it helps, you can think of as saying how much 0 and 1 there is in the state. A hallmark of a qubit is that when you look at its state, when you measure it, it will collapse to a classical state with some probability that's determined by those amplitudes. And quantum algorithms will use this phenomenon and other phenomena of qubits to achieve their computational advantage. Moving on, what's this deal with error correction? Well, nature gives us a lot of ways to produce qubits. It turns out you can do it by trapping atoms or ions or superconducting loops of wire and all sorts of fancy things. But the reason that we don't yet have a large-scale quantum computer is that these physical qubits are not entirely reliable. Well, actually, they're more than 99% reliable, but it's that 0.01% at the end that's going to kill you if your algorithm is running for millions of time steps. Fortunately, there is a way around this problem, and it's called quantum error correction. It's a very simple idea that says that if you take a large array, let's say, of many unreliable physical qubits, then you can use their redundancy to encode one reliable logical qubit. Quantum error correction is a foundational idea from a few decades ago, and it makes large-scale quantum computation possible in principle. Only recently has it become reality through developments in the surface code, the predominant quantum error correcting code used today. So let's move on to the last part here about the cost of control flow. And what we're talking about here is actually the time complexity of a quantum program. Let's imagine that we want to implement one of these quantum algorithms for search and optimization that I'm showing on the screen here. To achieve their promised asymptotic advantage, these algorithms will actually utilize operations over data structures, such as computing the length of a linked list. And we want to be able to do this in O of n time, as we would expect. If it were slower, we couldn't get that asymptotic advantage. In some prior work, we built a programming language that allows a developer to actually implement these sorts of operations as quantum programs that use familiar abstractions like control flow and recursion. We also showed that by taking a simple recurrence analysis of this recursive program, you can deduce that its time complexity should be O of n, as we would expect. But so far, all of that actually assumes ideal qubits. What happens on a realistic quantum computer that needs to use an error correction code? Well, it would be really nice if we could take that program, compile it down to physical operations operating on the code, count the number of logic gates that are going to be executed, and then see that its scaling is in fact linear as predicted. That would be really nice. It's not what happens. Okay? In fact, when you do this, you will see that the scaling of this program is quadratic rather than linear. That's an asymptotically worse result, which, if you think about it, is going to mean that the implementation of the program may not achieve the same asymptotic advantage that the quantum algorithm is claiming in the first place. So what causes this discrepancy, and how do we avoid it as programmers? Well, that's the question that we answer in this work. Our first contribution is to identify the cause of this overhead, which is in fact in the control flow in the program. The if-else statements are actually particularly costly under an error-corrected quantum computer. To help the developer reason about these costs, we present a cost model that repairs the recurrence analysis of the program to correctly account for the additional costs of error correction and correctly deduce, the O of n squared value. We then use this cost model to develop an automatic program optimizer called Spire that, when given the original quantum program, will recover an asymptotically efficient version of that program even when it executes under error correction. Before we continue, let's just take a moment to all get on the same page regarding some basics of quantum computation. So the principal operation that a quantum computer performs on individual qubits is called a quantum logic gate. On the slide here, we have a basic logic gate. It's the NOT gate. denoted x, which will take a 0 qubit, flip it to 1, or take a 1 and flip it back to 0. We're going to be seeing a lot of these diagrams on the right here, which are called quantum circuits. They're just sequences of quantum logic gates. Now, apart from these classical logic constructions like NOT, you can also do interesting quantum logic. For example, this Hadamard gate will take a 0 qubit and produce a superposition of 0 and 1. It will take a 1 qubit and also produce another superposition of 0 and 1 with a sign difference. That's right, the coefficients in these states can in fact be signed. And in this case, we'll call that sign difference a phase. One other thing that we're going to want to do is control the execution of a logic gate on the state of another qubit. This controlled NOT gate will flip the state of its second input only if its first input is equal to 1. Otherwise, it'll do nothing. We can generalize this to having multiple controls. This Toffoli gate will have 2 control bits. You can go even bigger and get these things that we can call multiply controlled NOT, or MCX gates, which we'll be seeing a lot more of. Now, we don't want to be writing literal logic gates all the time, so it helps to be able to develop language abstractions, like this assignment operator that will end up compiling down into logic gates. So here we have a program operating over 3 Boolean variables that's just going to assign one to another and then one to another, which will compile down to 2 C0 gates, one corresponding to each statement. Now, for some technical reasons, quantum algorithms will not in general want the state of a temporary variable, like the t variable in this program, to be non-zero at the end of a program. It turns out that when this is true, the quantum algorithm will in general give an incorrect result. And to resolve this issue, what you have to do is a process called uncomputation, which is essentially reversing the sequence of bit flips that happened on that temporary variable to restore it back to the 0 state by the end of the program. And we can reflect that in the program via this operator that I'm going to call unassignment. It is the exact opposite of the assignment operator. And in this case, it'll just compile to another C0 gate. Now, we don't want to have all of these arrows around, so it really helps to automate that with some structure. We're going to introduce this with do statement. And what it's going to do is it's going to execute the with block, then the do block, and then it will invert the contents of the with block to automate this whole uncomputation thing. The last program structure that we're going to want is control flow. So if we have an if statement, like this if statement over x and y with a statement inside, that's just going to compile to a controlled quantum logical gate, in this case, the Toffoli gate. Given all these ingredients, we can then put them together to see how a structured quantum program using control flow will eventually compile down to an explicit quantum circuit. All right, so that was all the background. Let's get to the main subject, which is the cost of control flow. So the question that we need to consider here is, how do we actually get a program to run on an error-corrected quantum device? Well, the chief thing that we need to do there is to take every logic gate in the program and find some physical way of realizing it as little physical operations on that error-correcting code. Now, we're not going to go over the details here, but for a subset of quantum logic gates, it's well known how to do this in the literature. This subset is called the Clifford gates, and it includes the C0 gate and the Hadamard gate that we saw earlier. Notably, it does not include many of the other gates that we would want, like these larger multiply controlled X gates. These gates cannot be realized directly on an error-corrected quantum computer. What you have to do is decompose them to smaller gates, and you can't actually decompose them to Clifford gates alone. You have to add a gate to your hardware gate set, which is called the T gate. What is this T gate? Well, here's its mathematical definition. It does nothing to 0, and to 1, it puts like a root of unity on it. Okay, this is the mathematical definition. Fortunately, we don't really need to understand that for this talk. All you really need to know is that given the T gate, what we can then do is take arbitrarily large MCX gates and use this recursive decomposition on the slide to turn them into Toffoli gates, which we can then write out as this sequence of Clifford gates and T gates. Okay. So far, I've been highlighting these T gates in orange. And the reason that I've been doing that is that even though T gates are possible to realize on an error-corrected quantum computer, they are very expensive to do so. How expensive? Here's a figure from a paper from some folks at Google that depicts the physical operations required to realize C0 gates and Hadamard gates on the surface code. Now, you don't need to understand the details of what this diagram means, but the shapes, the volumes of the gray blobs in the picture give you an idea of how complex it is to physically realize each of these gates. So what about that T gate? Well, if you look at the diagram, one thing you'll see is that it's got these two little protrusions going into the back of the page. Where is that going? Are you ready? It goes here. Okay. This picture depicts the complexity of realizing a T-gate on a surface code error-corrected quantum computer. And what it really emphasizes is, yes, you can implement this gate, but it costs about 100 times more than any Clifford gate in your system, which means that it rapidly dominates the cost of your quantum algorithm. This domination has been the cause of quantum algorithm designers studying T complexity, where the number of T gates of a quantum computation is the dominant factor in how well it performs under error correction. Now, how does that apply to our case? Well, one thing we can show is that a large MCX gate with a lot of control bits requires a proportional number of T gates in order to realize. And what this means for our programs is that programs with deeply nested control flow that compile to a lot of control bits end up being a lot more expensive to realize. Let's bring that all the way back to our running example in the length program. How do we explain that asymptotic discrepancy from earlier? Well, one thing we need to understand is that for the compiler to take the program on the left and compile it to a circuit, the first thing that it has to do is unroll the recursion, exposing this nested structure of if-else statements, translate each one of those statements to a circuit, at which point we will observe that despite the program having only length, say, O of n, the number of control bits will scale as O of n squared. This is, in fact, the explanation of the discrepancy in the graph that we saw in the beginning. Cool. So now that we have a better understanding of the cost of control flow, let's see how we can help the developer reason about it through our cost model. The idea here is that we want to be able to take the syntax of a program and produce a function that just computes its T complexity, right? It tells us that the way that it should scale on the error-corrected device is O of n squared. To do this, it turns out that we're also going to want to define a function for the MCX complexity, or the number of MCX gates to which the program compiles. Let's study this simpler case first. So there are some base cases. They're not too interesting, skip and composition of programs. The interesting case is for if statements. How many MCX gates does an if statement compile to? Well, the answer turns out to be that when you wrap a statement in an if, what you're doing is you're adding a layer of control dots to every gate in the body of the if. The width of this picture is not changing, though. The number of MCX gates is staying the same. So that will be our definition for MCX complexity. It is different from the definition we'll use for T complexity, which in this case is going to actually count every single dot. All right, so in this case, we're going to define the T complexity of if as being the T complexity of the body of the if plus some multiple of the width of this picture, or the MCX complexity. So what's the upshot of this math here? Well, it actually allows us to repair the recurrence analysis of the program from the beginning to add terms that correctly account for the additional T complexity of performing control flow at every level in the recursive call tree of the program. And you can prove that performing this analysis will give you the correct T complexity of the algorithm. But that's actually not the only thing that the cost model does for us, because it also allows us to automatically optimize programs, rewrite them to lower their T complexity. One of the first optimizations we can perform is something called conditional flattening. As the name suggests, it works with these nested, deep sequences of if statements and flattens them down. Right? When you have these deeply nested if statements that would compile to a lot of control dots, one thing you can do is actually just pre-compute the conjunction of all of the if statements, cache that once, uncompute it once at the end, and this actually gives you an asymptotic improvement. If you have n levels of nesting and the statement S on the inside has length k, this takes the T complexity from O of nk to O of n plus k. Right? So apart from this asymptotic improvement, you can also get some constant improvements. Here's an optimization called conditional narrowing. What's going on in this case is that we've got a program that is executing a statement S1, then S2, and then it's uncomputing S1. It's executing the inverse of S1. It takes a while to see this, but in cases like these, it is always safe to unconditionally execute the statement S1 and its inverse. Okay, this will actually not affect the correctness of the program at all, but it will save a lot of control bits. Okay? So by putting together the two optimizations that we just saw, conditional flattening and narrowing, on our simple example program from the beginning with all of these control dots, the result is that, well, the optimized program has a lot fewer control dots. Okay? And how does this apply to our length example from the beginning? Well, the original program has O of n squared T complexity, And by running our implementation that automatically performs these two program rewrites, we get a new version of the program that only has O of n t complexity, the asymptotically optimal version. So how well does this work in practice, right? What we did to evaluate the Spire compiler was that we used a series of 11 benchmarks that utilize operations over quantum data structures from some of our prior work. As we saw just earlier, Spire is able to reduce the t complexity of the program from O of n squared to O of n in the case of the length program. You can see our paper for our full suite of benchmarks. An important question that we also want to ask is, how does this compare to existing quantum circuit optimizers from the literature that have been a focus of research at PLDI and other communities in recent years? Well, the answer is that we evaluated Spire against 8 existing quantum circuit optimizers, and we found that 6 of them did not produce an asymptotically efficient circuit. They still yielded a quadratically sized rather than a linearly sized one. Okay, so what about the 2 that did, right? How do we compare? In comparison, Spire produces similar performing programs, but with much reduced compile time. In this case, we could do it in about 2400x faster. Now, why is that? The intuition is because these existing quantum circuit optimizers have a really hard job. They're given an asymptotically large circuit and have to crunch it down to a small one. Whereas what Spire can do is just do some simple program rewrites at the high level, then do some code generation and produce a much smaller circuit to begin with. Okay, so let's wrap up. The problem that we studied in this work is that programming with abstractions like control flow on a quantum computer with error correction is going to be very costly. And to address this problem, we introduce a cost model and some optimizations to help developers reason about and reduce these costs. Moving forward, there's a lot of opportunity here to improve quantum circuit optimizers by exploiting the kinds of program structure that we identified in this work. Now, if you're curious, so far we've been talking about one specific error correction code, the surface code. In the paper, we have a discussion about how these costs and techniques will apply to other codes. There are other improvements that we can do, other things that quantum algorithm developers are doing right now by hand that we can import into automatic compilers, which leaves open a question of, are there programs that fundamentally can't be optimized this way to get an asymptotic improvement and will always remain some kind of bottleneck under error correction? So if there's one takeaway from this talk, is that the interface between quantum programs and the error-corrected hardware on which they're going to run is going to be really key for us to study to develop more expressive and efficient programming abstractions for quantum computing. Thank you.
Thank you, Charles. We have time for, I think, one question. And I'm happy to ask it since nobody's at the microphone. I understand that T-count is obviously important for error correction. And I understand that, using this control flow, you can, in other words, doing the control flow analysis, you can dramatically reduce the number of MCX gates. What I don't understand is, why is this specifically for error correction as opposed to 4 higher level languages that have if then else and similar constructs?
Yeah, I think that's a good point that you make, right? There is an alternative framing here where we generalize the interpretation of our techniques to just higher level constructs in general. Yeah. In this work, we chose to focus on error correction because we really wanted to help algorithm developers who spend every single day computing the T complexities of their programs. And we wanted to give them a way to reason about how higher level abstractions will specifically apply to the algorithms that they're trying to write.
Okay, but you think it's actually more general than that?
Yeah, I think there's a world in which we can think about these techniques more generally. Yeah.
Okay, great. Let's thank Charles again.